Welcome, cosmic explorers. Today, we're embarking on an extraordinary journey across the universe, not just to see stars, but to truly understand them. We're going to witness the most extreme physics and staggering scales our cosmos has to offer, from the tiniest, coolest stellar embers to gargantuan celestial furnaces and beyond. We'll uncover 18 different types of stars and stellar objects, each more mind-blowing than the last, pushing the very boundaries of what we thought possible. Get ready to have your perspective on the universe fundamentally shifted. Our cosmic tour begins with the red dwarf. These are the smallest and most numerous stars in our galaxy, weighing in at just 0.08 to 0.6 times the mass of our Sun. Don't let their size fool you, they are incredibly long-lived, burning their fuel at a snail's pace. Their surface temperature hovers around a relatively cool 2,500 to 5,000 Kelvin, making them dim compared to other stars. But here's the kicker: a red dwarf can live for trillions of years, far longer than the current age of the universe. They are the universe's ultimate energy savers. Next up, we scale slightly larger to the orange dwarf. These stars are a bit more energetic than their red counterparts, typically ranging from 0.7 to 0.9 times the mass of our Sun. Their surface temperatures are warmer, usually between 4,000 and 5,200 Kelvin. While not as long-lived as red dwarfs, they still boast impressive lifespans, often reaching 15 to 30 billion years. This extended stellar life means they have ample time for planets to form and potentially evolve life, making them interesting candidates for exoplanet searches. It's a step up in heat and size. Now, we arrive at a star you know well, our very own Sun, a yellow dwarf. At one solar mass, it's a perfectly average star, burning hydrogen into helium at its core. Its comfortable surface temperature of approximately 5,778 Kelvin provides the warmth essential for life on Earth. Our Sun has a lifespan of about 10 billion years, and it's currently halfway through its journey. While seemingly benign, the Sun is a dynamic powerhouse, regularly unleashing colossal solar flares and coronal mass ejections, electromagnetic storms powerful enough to disrupt technology across vast distances. It's a gentle giant, but one with a temper. What happens when a star like our Sun runs out of fuel? It sheds its outer layers and collapses into a white dwarf. These stellar remnants are incredibly dense, packing about 0.5 to 1 point for solar masses into a sphere roughly the size of Earth. Their surface temperatures can range from a scorching 8,000 up to 100,000 Kelvin, initially, but they slowly cool over billions of years. Imagine a teaspoon of this matter, it would weigh around 5.5 tons. This extreme density means matter is crushed to incredible pressures, with electrons providing the only outward push, preventing further collapse. It's a star's dying ember, but still fiercely hot. Now for something theoretical, the blue dwarf. This isn't a star type we've observed yet, because the universe simply isn't old enough. It's hypothesized to be the future of red dwarfs, after they've exhausted virtually all their hydrogen fuel over trillions of years. Without fusion, these stars would slowly contract and heat up, changing from red to blue as their surface temperature increases. They would be incredibly long-lived and cool very slowly, eventually becoming white dwarfs. This is a glimpse into a cosmic future so distant, it's almost beyond our comprehension, a truly ultimate extreme of stellar longevity. Stepping back down in mass, we encounter the brown dwarf, often called a failed star. These objects are too massive to be planets but not massive enough to ignite stable hydrogen fusion like true stars. They typically range from 13 to 80 times the mass of Jupiter. Their internal temperatures, around 2000 Kelvin, are just hot enough to briefly fuse deuterium, a heavier isotope of hydrogen, but not sustained hydrogen fusion. Lacking a strong internal heat source, they slowly cool and fade over billions of years. They emit mostly infrared light, making them difficult to detect, a shadowy presence lurking between planets and stars. Now, let's look at subdwarfs. These are main-sequence stars, much like our Sun, but they have extremely low metallicity. In astronomical terms, metals refer to any element heavier than hydrogen and helium. These stars formed very early in the universe's history, before heavier elements were widely forged in supernovae. This low metallicity means they are older, less luminous, and slightly smaller than normal main-sequence stars of the same mass, with surface temperatures ranging from 4,500 to 7,000 Kelvin. They are ancient relics, whispering tales from the dawn of time, offering clues to the early universe's composition. Prepare for a serious escalation in scale. Next, we have blue giants. These are massive, luminous stars, typically 10 to 100 times the mass of our Sun, with surface temperatures soaring between 10,000 and 30,000 Kelvin. They burn through their fuel at an astonishing rate, leading to incredibly short lifespans of only 10 to 100 million years. This is a mere blink in cosmic time compared to our Sun. Their intense radiation pushes against their outer layers, making them swell to enormous sizes. They are the true heavyweights of the main sequence, shining with a brilliant, fierce blue light. What happens when a star like our Sun exhausts its core hydrogen? It expands dramatically into a red giant. This is our Sun's ultimate fate. As hydrogen fusion ceases in the core, the star begins fusing hydrogen in a shell around the core, causing its outer layers to cool and swell. A red giant can be hundreds of times larger than our Sun, engulfing Mercury, Venus, and possibly even Earth. Despite their enormous size, their surface temperatures are relatively cool, around 2,500 to 5,000 Kelvin, giving them their characteristic red hue. This stellar expansion is a terrifying glimpse into our solar system's distant future. If a blue giant is massive, a blue supergiant is simply colossal. These stars are among the most luminous and hottest objects in the universe, weighing 10 to 70 times the mass of our Sun and sporting surface temperatures of 10,000 to 50,000 Kelvin. Their lifespans are shockingly brief, sometimes lasting only a few million years. They are so massive and burn so intensely that they are constantly losing mass through powerful stellar winds, shedding their outer layers into space. These titans live fast and die young, often ending their lives in spectacular supernova explosions, seeding the cosmos with heavy elements. And now, for pure, mind-boggling size, the red supergiant. These are the largest stars by volume in the universe, true cosmic behemoths. They can expand to thousands of times the radius of our Sun, with some so large that if placed in our solar system, their outer layers would extend past the orbit of Jupiter. Despite their immense size, their surface temperatures are relatively cool, around 3,500 to 4,500 Kelvin. They burn through their fuel incredibly quickly, lasting only a few million years before dramatically collapsing into a supernova. Betelgeuse is a famous example, a red giant star visible in the night sky, awaiting its fiery end. Beyond the supergiants, we find the hypergiants, the undisputed kings of stellar size. Scuti, a famous example, is one of the largest stars known, estimated to be up to 1,700 times the radius of our Sun. If Scuti replaced our Sun, its outer edge would extend beyond the orbit of Jupiter, perhaps even Saturn. This star is so enormous that light would take over 7 hours to travel around its circumference, compared to just 14.5 seconds for the Sun. Its surface temperature is around 3,365 Kelvin. Hypergiants are incredibly unstable, often shedding vast amounts of their mass through powerful stellar winds and pulsations. They represent the absolute limit of how big a star can get before tearing itself apart. Wolf-Rayet stars are true cosmic outliers, incredibly hot and luminous, with surface temperatures ranging from 30,000 to 200,000 Kelvin. These are massive stars, typically 10 to 250 times the mass of the Sun, that have shed their outer hydrogen layers, exposing their hot, helium-rich cores. They have incredibly powerful stellar winds, blowing away mass at speeds of thousands of kilometers per second. This rapid mass loss creates spectacular nebulae around them. Wolf-Rayet stars are thought to be in the very late stages of their evolution, rapidly approaching a catastrophic end as a type Ib or icy supernova, leaving behind either a black hole or neutron star. They are cosmic fireworks, before the ultimate explosion. When a massive star collapses in a supernova explosion, if it's not quite massive enough to form a black hole, it leaves behind a neutron star. These objects are mind-bogglingly dense. Imagine cramming 1.4 to 3 times the mass of our Sun into a sphere only about 20 kilometers across, the size of a city. Their surface temperature can be millions of Kelvin initially, slowly cooling. Here's the terrifying detail: a single teaspoon of neutron star material would weigh about 6 billion tons. Yes, that's 6 billion tons. The gravitational pull is so intense that the star's atoms are crushed, forcing protons and electrons to merge into neutrons. This is matter pushed to its absolute limits. Many neutron stars are also pulsars. These rapidly spinning neutron stars emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space, and if one of them happens to point towards Earth, we observe it as regular, precisely timed pulses, like a cosmic lighthouse. Pulsars can spin incredibly fast, some rotating hundreds of times per second, with almost perfect regularity. The precision of their pulses is so astounding that some are more accurate than atomic clocks. They are the ultimate cosmic timekeepers, a testament to the extreme physics of a collapsing star. Even more extreme are magnetars, a type of neutron star with an unbelievably powerful magnetic field, billions of times stronger than any magnet we can create on Earth. Their surface temperatures are millions of Kelvin. These fields are so intense that if a magnetar were within 1,000 miles of Earth, it would literally wipe every credit card, erase every hard drive, and likely cause atoms to deform on a molecular level due to the immense magnetic stress. The magnetic field can tear the star's crust, causing starquakes that release incredible bursts of X-rays and gamma rays, making them among the most luminous objects in the universe for a fraction of a second. This is magnetism taken to its ultimate, terrifying extreme. And now, we arrive at the most enigmatic and terrifying objects in the universe: black holes. Formed from the core collapse of the most massive stars, these are regions of space-time where gravity is so intense that nothing, not even light, can escape. They have no surface temperature as they have no surface. The boundary beyond which escape is impossible is called the event horizon. Once you cross this point, you're on a one-way trip to the singularity at the center, where all mass is crushed into an infinitely small, infinitely dense point. The physics within a black hole defies our current understanding, representing the ultimate triumph of gravity. It's a cosmic abyss, consuming all that dares to come close. Finally, we venture into the realm of the truly theoretical, the Quark star. This is an even denser, more exotic object, hypothesized to form from the most massive neutron stars after they collapse further, but before becoming a black hole. In a quark star, the immense pressure and density would be so extreme that the individual neutrons themselves would break down into their constituent particles, up and down quarks, forming strange matter or quark matter. This is matter in a state utterly unlike anything we normally encounter, potentially existing at densities even higher than neutron stars. If they exist, quark stars would represent another terrifying extreme, a stepping stone to the singularity, defying our everyday physics. What an incredible journey we've taken! From the tiny, long-lived red dwarfs to the scorching blue supergiants, the city-sized neutron stars with their terrifying density and magnetic fields, all the way to the enigmatic black holes and theoretical quark stars. We've witnessed a universe of staggering scale, extreme temperatures, and physics that constantly challenges our imagination. Each stellar object, whether a familiar yellow dwarf or an exotic magnetar, plays a crucial role in the cosmic cycle, shaping the universe we see today. The cosmos is truly a place of endless wonder and terrifying beauty. Thank you for exploring these cosmic extremes with us.